It's Professor Dave. Let's learn the substitution rule.
He knows a lot about all kinds of stuff. Professor Dave explains.
Hopefully we've gotten used to integration by now, and even feel that integrating polynomials is very easy as taking a derivative. This is because integrating a simple polynomial, much like taking a derivative, will follow a simple algorithm that never changes. But this will not always be the case, as integration doesn't always follow such a rigid algorithm. And in fact, there will be times where it is not immediately obvious how to do it. In such a case, there are a few tricks we can use, and the first one we will learn is called the substitution rule. The substitution rule allows us to take a complicated integrand and simplify it by representing some portion of it with the letter u. Take this problem, the integral of 2x times cosine x squared plus 1. This looks like a mess. The cosine is operating on a sum, and it is also part of a product, so nothing we have learned so far will work here. But let's try something clever. What if we make a substitution? Let's replace x squared plus 1 with the letter u. We are still saying the same thing, since u equals x squared plus 1, but we are simplifying the integrand this way, because if cosine is operating on a lone variable rather than an expression, we will be able to integrate it. The only problem is that if we are changing things to u, this dx will be a problem. We need things in terms of u now, so we need this to be du instead. But we can fix that. Let's understand that d over dx of x squared plus 1, or the derivative of this function with respect to x, is 2x. Now we can do something tricky. Let's bring the dx up to the other side to get 2x dx. This may seem strange, as dx is simply part of the notation d over dx, and it may not look like something we can manipulate algebraically. Later in this series, we will justify why this is possible. For now, let's just do it and observe how this is useful. Now we can understand that this function on the left is what we are representing as u, so let's just change that to u. And we therefore see that du equals 2x dx. That's quite convenient, because lo and behold, if we bring the 2x inside the integrand to the other side of this cosine term, we have 2x dx right here. So according to this equation, we can just rewrite that as du. Now that we have a differential du that agrees with the rest of the integrand, we are ready to integrate, and cosine u du can be integrated just like cosine x dx, or cosine z dz, or cosine smiley face d smiley face. The variable doesn't matter. The integral of cosine u du is sine u plus c. Now that integration is complete, let's return u back to its original form, and we have sine of x squared plus 1 plus c. And that's the answer. Just to be thorough, let's differentiate this and make sure we get what we started with. C will go away, so it's just sine of x squared plus 1. According to the chain rule, we do the outer function first, so we get cosine x squared plus 1 times the derivative of what's inside, which is 2x. That is indeed what we started with, so this approach worked like a charm. In this way, we can think of the substitution rule as the chain rule in reverse, because we symbolize some piece of the function with a single variable, allowing us to integrate more simply, just the way that the chain rule ignores the inner function during the first step of differentiation. The only thing to remember is that while the chain rule will always work, the substitution rule won't always work. It only worked here because our expression for du was indeed present in the integrand, because the integrand was in the form f of g of x times g prime of x. If this wasn't the case, we couldn't do this, so we have to be able to look at an integral and recognize whether or not the substitution rule can be applied. If we do have an integrand in the form of f of g of x times g prime of x dx, we can represent g of x as u, g prime of x dx turns into du, and we end up with f of u du, which we can then integrate. Here's another example. X squared times the square root of x cubed plus 1. Is this in the form that we mentioned? If the square root is f and what's inside is g, that does look like f of g of x. But what about g prime? Well, g prime would be 3x squared, and we pretty much have that, so let's give this a try and see what happens. Let's change x cubed plus 1 into u, so that we have root u. Now du over dx, which means that we are differentiating the expression that u represents with respect to x, will equal 3x squared. That means that du equals 3x squared dx. Now, it's true that we don't have 3x squared dx, but that's no problem. We have x squared dx, so let's just bring the 3 over to the other side. X squared dx will then equal du over 3, or 1/3 du. So let's write 1/3 du in its place. Now things are looking pretty good. Let's pull 1/3 out of the integral, and then we can integrate root u du. Remember, that's u to the 1/2, so it will become u to the 3/2 over 3/2, or 2/3 u to the 3/2, times the 1/3 we already had, and that will be 2/9 u to the 3/2. Now we can return u to its original form, and we have 2/9 times the quantity x cubed plus 1 to the 3/2 power, and then plus c, as we are used to. Let's do a couple with trig functions. How about sine to the 6th x times cosine x dx? The sine term has more going on with it, so why don't we try representing sine x as u? Remember, sine to the 6th x just means the quantity of sine of x raised to the 6th power. So this just becomes u to the 6th. Then du over dx equals cosine x, so du equals cosine x dx. That is indeed present, so let's just make the rest of this equal to du, and we are ready to go. Integrating u to the 6th gives us u to the 7th over 7. We return u to its original form, and we get sine to the 7th of x over 7 plus c. Now, how about tangent x dx? This is an example where substitution might not jump out immediately as a possible strategy. But if we remember that tangent is sine over cosine, and that the derivative of cosine is negative sine, then we might see a plan unfold. Let's use cosine x as our u, and that means du will be negative sine x dx. We have positive sign, so let's make this negative du, and then pull the negative sign out. Now du over u is the same as 1 over u times du, and we know that the integral of 1 over u will be the natural log of u. The only thing is that we have to put u in absolute value brackets, because this value will sometimes be negative, as it's a cosine function, and we know that the natural log can't take negative values. So we get negative natural log of the absolute value of u plus c, and then change u back to cosine, and that's our answer. So remember, anytime we are integrating some function, and the function can be split up into a smaller function followed by the derivative of that smaller function, or something very close to it, the substitution rule is a good idea for something to try. This won't always work, but if it does, it can take a complicated integral and make it very simple. So it is definitely a great start to our bag of tricks for integration. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.